The introduction of the scientific paper titled, Molecular Architecture of Multiblock Copolymers Synthesized by the Chain Shuttling Technology, provides an overview of the recent advances in the characterization of ethylene, 1-octene-based statistical multiblock copolymers, MBCs, synthesized via chain shuttling copolymerization. The introduction focuses on the peculiarities of MBC systems, specifically the non-uniform chain architecture due to compositional heterogeneity at the inter- and intra-chain level. The paper discusses the effect of dispersity on the phase behavior and properties of MBCs, including the consequences of crystallization on microphase separation, domain spacing, and morphology. Additionally, the introduction highlights the importance of elucidating the chain microstructure of MBCs in terms of average block length and block length distribution. The paper emphasizes the use of various techniques, such as solvent and thermal fractionation, transmission electron microscopy, and small-angle X-ray scattering, to characterize the inter- and intra-chain heterogeneous composition of MBCs. Finally, the introduction provides guidelines on establishing structure-properties relationships for polydisperse MBC systems. It also briefly discusses the synthetic routes for producing block copolymers and introduces the chain shuttling copolymerization technology used in the synthesis of the MBCs discussed in the paper. Figure 1 in the paper illustrates the chain shuttling copolymerization (CSC) scheme used to synthesize olefin-based statistical multiblock copolymers, MBCs. The figure shows the two organometallic catalysts, Cat1 and Cat2, with different comonomer reactivity ratios, as well as the chain shuttling agent, CSA, that exchanges its coordinated dormant chains with the growing polymeral chains linked to the metallic centers. In the presence of a mixture of ethylene and 1-alkene, such as 1-octene, the CSC process leads to the formation of statistical multiblock copolymers characterized by alternating hard, C8-poor, and soft, C8-rich, blocks. The bottom part of Figure 1 shows the resulting multiblock copolymers, which are constituted by alternating hard and soft blocks of non-uniform length. The significance of Figure 1 to the paper is that it provides a visual representation of the CSC process, highlighting the key components involved in the synthesis of MBCs. It also emphasizes the non-uniform chain architecture of MBCs, which is a result of the compositional heterogeneity at the inter- and intra-chain level. The figure demonstrates the complex nature of MBCs and sets the stage for discussing the subsequent sections of the paper, which focus on the effects of dispersity, chain microstructure, and compositional heterogeneity on the phase behavior, properties, and characterization techniques of MBCs. It is worth noting that there are no other figures mentioned in the text that would be useful to discuss. Figure 2 shows the chemical structure of bis, phenoxyimine, ZR, Cat1, and pyridylamido, HF, Cat2, complexes, which are suitable for the synthesis of olefin-based statistical multiblock copolymers, MBCs, via chain shuttling copolymerization, CSC. These MBCs are characterized by alternating hard, C8-poor, and soft, C8-rich, blocks of non-uniform length. The figure also illustrates the resultant statistical multiblock copolymers constituted by the alternation of hard and soft blocks. The significance of Figure 2 to the paper is to provide the chemical structures of the catalysts used in the synthesis of MBCs via CSC and to demonstrate the control over the composition and architecture of the MBCs, which is crucial for understanding their structure-properties relationships. The figure highlights the ability of the chain shuttling technology to synthesize MBCs with tailored molecular architecture and composition, leading to unique properties and potential applications in various fields. Figure 3 of the paper illustrates the effect of hard block content on the thermal and mechanical properties of multiblock copolymers synthesized via chain shuttling copolymerization. The figure shows the stress-strain curves for different multiblock copolymer samples with varying hard block content. The samples exhibit strain hardening and high ductility, with the stress and strain at break increasing with increasing hard block content. Additionally, the Young modulus decreases with decreasing hard block content. These results indicate that the properties of the multiblock copolymers can be tuned by adjusting the hard block content. The figure also highlights the differences in mechanical properties between multiblock copolymers and conventional random copolymers with similar composition. The multiblock copolymers exhibit higher modulus and stress at any strain, as well as higher ductility, compared to the random copolymers. These findings demonstrate the potential of multiblock copolymers synthesized via chain shuttling copolymerization for achieving superior mechanical properties. Figure 4 in the paper describes the phase diagram of low-dispersity D-block copolymers XY, which consists of thermodynamically incompatible blocks. The phase diagram shows the regions of stability for various equilibrium morphologies, such as spheres arranged in a body-centered lattice, close-packed structures, hexagonally packed cylinders, and lamellae. The phase diagram also shows the effect of volume fraction and interaction strength on the type of nanostructure that forms. The significance of Figure 4 to the paper is that it provides a visual representation of the different morphologies that can be achieved in low-dispersity D-block copolymers. This information is important for understanding the phase behavior and properties of multiblock copolymers synthesized via chain shuttling copolymerization. It also provides a basis for further analysis of the chain microstructure and its impact on the properties of these materials. Additionally, the paper mentions other figures such as Figure 3, which illustrates the relationship between the melting temperature and density of ethylene, 1-octene random copolymers and multiblock copolymers. This figure is significant because it highlights the unique properties and behaviors of multiblock copolymers compared to random copolymers. Figure 5 shows the melting behavior of ethylene, 1-octene multiblock copolymers with different hard block content. The x-axis represents the weight percentage of the hard block, while the y-axis represents the melting temperature. The figure includes data for copolymers with different molecular weights and dispersity indices. The significance of Figure 5 is that it demonstrates the effect of the hard block content on the melting behavior of the multiblock copolymers. It shows that as the weight percentage of the hard block increases, the melting temperature also increases. This indicates that the presence of the hard block has a significant impact on the thermal properties of the copolymers. The results from Figure 5 can be used to understand the relationship between the molecular architecture of the multiblock copolymers and their thermal behavior. It provides valuable insights for designing copolymers with specific thermal properties by controlling the composition and content of the hard block. Additionally, it highlights the importance of accurately characterizing the composition and structure of the multiblock copolymers to understand their properties and performance. It is worth noting that there are no significant results or conclusions mentioned specifically for Figure 5 in the given text. Figure 6 of the paper shows the domain spacing, DDS, of olefin-based nearly low-dispersity D-block copolymers, open symbols, and disperse D-block in multiblock copolymers synthesized via coordinative chain transfer polymerization, CCTP, and chain shuttling copolymerization, CSC, respectively, filled symbols, as a function of the molecular mass of the constituent D-block units, MNDI. The figure demonstrates that the domain spacing increases with increasing the molecular mass of the D-block units. The trend follows a power law dependence, with DDS approximately equals MNDI 2/3. This result is significant as it indicates that the molecular mass of the blocks plays a crucial role in determining the domain spacing and, therefore, the microphase separation behavior of the copolymers. It suggests that controlling the molecular mass of the constituent blocks can be a valuable strategy for tailoring the phase behavior and properties of multiblock copolymers synthesized via chain shuttling copolymerization. Figure 7 presents TEM images of 2 MBC samples with different molecular weights. The images show the solid-state morphology of the MBCs after slow cooling from the melt. The sample with a higher molecular weight, EO155, exhibits well-defined lamellar sheaves with round domains scattered throughout. In contrast, the sample with a lower molecular weight, EO86, shows a more homogeneous arrangement of lamellar structures without round domains. The significance of Figure 7 is that it demonstrates how the molecular weight of MBCs can influence their solid-state morphology. The presence of round domains in the higher molecular weight sample suggests a phase-separated morphology, while the absence of round domains in the lower molecular weight sample indicates a more homogeneous lamellar arrangement. This highlights the importance of considering the chain microstructure, including molecular weight, when studying the properties and structure of MBCs. Figure 8 of the paper shows the crystallization modes for a semicrystalline block copolymer containing one crystallizable block. The figure presents 5 different crystallization modes. A. Unrestricted crystallization. B. Crystallization preceded by microphase separation. C. Disruption of microphase-separated morphology due to crystal growth. D. Crystallization occurring within phase-separated domains. And E. Pass-through crystallization. These modes depend on the thermodynamic conditions, such as the order-disorder transition temperature, the crystallization temperature, and the glass transition temperature. The figure highlights the importance of the state of the melt before crystallization in determining the solid-state morphology and properties of the multi-block copolymer. Understanding these crystallization modes can provide insights into the structure-property relationships of these complex systems. Figure 9 in the paper shows the X-ray diffraction profile of an ethylene, 1-octene multiblock copolymer synthesized through chain shuttling copolymerization. The diffraction pattern indicates the presence of the orthorhombic form of polyethylene (PE) crystals, as evidenced by the 110 PE and 200 PE reflections. This confirms the semicrystalline nature of the copolymer. The significance of this figure lies in the characterization of the solid-state morphology of the multiblock copolymer, specifically the presence of crystalline domains. This information is important for understanding the properties and behavior of the copolymer, as well as its potential applications. Figure 10 shows the melting and glass transition temperatures of MBC samples compared to conventional statistical copolymers with similar comonomer content. The figure demonstrates that MBCs have higher melting temperatures and glass transition temperatures compared to their random copolymer counterparts. The figure also shows that the properties of MBCs can be tuned by adjusting the hard block content. The significance of Figure 10 is that it highlights the superior thermal properties of MBCs compared to random copolymers. The higher melting temperatures of MBCs make them suitable for applications where high temperature stability is required. Additionally, Figure 10 provides insights into the relationship between the hard block content and the thermal properties of MBCs. It shows that increasing the hard block content leads to higher melting temperatures and glass transition temperatures. In conclusion, Figure 10 demonstrates the improved thermal properties of MBCs compared to random copolymers and highlights the impact of the hard block content on these properties. It provides valuable information for designing MBCs with desired thermal properties. Figure 11 in the paper shows stress-strain curves and the values of the Young modulus for an MBC multiblock copolymer sample compared to a conventional statistical copolymer. The MBC sample has a non-uniform chain architecture due to the compositional heterogeneity occurring at inter- and intra-chain level. The figure illustrates that MBCs have superior mechanical properties, such as higher Young modulus and stress at break, compared to the random copolymer. The results also show that the hard block content in MBCs plays a significant role in determining the mechanical properties. Additionally, the MBC sample exhibits strain hardening and high ductility, even at high temperatures and deformations. This figure highlights the importance of the chain microstructure and composition in determining the properties of MBCs. Figure 12 shows stress-strain curves for multiblock copolymers, MBCs, with different molecular properties. The MBCs have similar C8 content in the hard and soft blocks but vary in terms of molecular mass and block length. It is observed that MBCs with higher molecular mass and more blocks exhibit greater mechanical resistance and higher ductility at 25 degrees Celsius. However, at 60 degrees Celsius, the MBCs with lower molecular mass and fewer blocks show a significant decrease in ductility. These results indicate that the chain microstructure, including block length and number of blocks per chain, significantly affects the mechanical properties of the MBCs. In the scientific paper shows TEM images of a MBC sample with a mass average molecular mass of approximately 90 kDa, with a C8 content of approximately 1 and 22 mol% in the hard and soft blocks, respectively. The sample was isothermally crystallized at 108 degrees Celsius after fast cooling the melt from 180 and 130 degrees Celsius. The images reveal the formation of bundle-like aggregates spreading all over the area. The size and number of crystals are observed to be larger for the samples quenched from a heterogeneous melt compared to those from a homogeneous melt. This indicates that at a crystallization temperature of 108 degrees Celsius, the crystallization of the sample quenched from a homogeneous and a heterogeneous melt occurs almost unrestricted, with the crystallization rate being higher than the rate of mesophase separation. Additionally, TEM images of samples crystallized at 115 degrees Celsius show similar solid-state morphology for samples quenched from both a homogeneous and a heterogeneous melt, with sporadic crystalline aggregates of small size spread in a matrix rich in soft blocks. The size and number of crystalline aggregates are observed to be greater for the samples quenched from a homogeneous melt compared to those from a heterogeneous melt. This difference is attributed to the lower crystallization rate for the sample crystallizing from a heterogeneous melt. In the paper presents master curves obtained by measuring the storage, G, and loss, G, moduli at different temperatures for an MBC sample with a mass average molecular mass of 250 kDa. AC8 content of approximately 2 and 36 mol% in the hard and soft blocks, and a hard block content of 18 Wt%. The curves are horizontally translated with respect to the reference data measured at 220 degrees Celsius. The corresponding TEM image shows the epitaxial crystallization of the hard blocks onto benzoic acid, Ba, resulting in the formation of oriented lamellae. The crystalline lamellae are stacked with the normal parallel to a common direction. This confirms the mesophase separation in the solid-state morphology and the formation of a mesophase-separated morphology reminiscent of the melt morphology upon quenching. In the paper shows TEM images and viscoelastic moduli master curves of 2 MBC samples with similar chain microstructure but different mass average molecular mass of approximately 155 kDa, EO155, and 86 kDa, EO86. The samples have a C8 content of approximately 0 and 20 mol% in the hard and soft blocks, respectively, and a hard block content of approximately 27 Wt%. The TEM images obtained by slow cooling from the melt to room temperature show PE lamellar sheaves typical of spherolytic superstructures for both samples. However, the EO155 sample exhibits brighter round domains within the sheaves compared to the EO86 sample. This indicates mesophase separation in the solid state for the EO155 sample and a more homogeneous lamellar arrangement for the EO86 sample. The difference in solid-state morphology can be attributed to the higher length of the soft blocks for the EO86 sample and the presence of additional PE lamellae that cross the matrix rich in soft blocks and connect neighboring domains rich in hard blocks, forming a web-like structure for the EO155 sample. The significance of these results is that they provide insights into the solid-state morphology of MBC samples with different chain microstructures and molecular masses. The observed differences in crystal size, number, and arrangement are attributed to the effects of crystallization temperature, melt composition, and the length of the hard and soft blocks. These findings contribute to a better understanding of the structure-property relationships in MBCs and can guide the design of new MBC materials with tailored properties. Figure 16 shows the TEM image of an MBC sample with a high molecular mass, 155 kDa, and a low molecular mass, 86 kDa. The TEM image reveals the solid-state morphology of the MBC samples after crystallization. For the high molecular mass sample, the image shows spherolytic superstructures with bright round domains embedded in the matrix. These bright domains indicate the crystallization of the hard blocks in separated domains. In contrast, the low molecular mass sample exhibits a more homogeneous arrangement of lamellar structures. This difference in morphology is attributed to the different chain microstructures of the two samples, with the high molecular mass sample containing long hard blocks that tend to crystallize in separated domains. Figure 17 of the paper shows TEM images of two MBC samples with different molecular masses and similar chain microstructures. The image on the left, Fig. 17a, shows a sample with a high molecular mass, where the sheaves of PE lamellae are spotted by bright round domains. These round domains indicate mesophase separation in the solid state, with the long hard blocks crystallizing in separated domains. The image on the right, Fig. 17b, shows a sample with a low molecular mass, where the lamellar arrangement is more homogeneous, without the presence of round domains. This suggests a more uniform distribution of lamellae in the sample. The significance of Figure 17 is to highlight the influence of molecular mass on the solid-state morphology of MBCs, with higher molecular mass leading to the formation of separated domains, while lower molecular mass results in a more homogeneous lamellar arrangement. This information is important for understanding the structure properties relationships of MBCs and for tailoring their properties based on the desired application requirements. Figure 18. The TEM images of MBC samples with high, EO155, and low, EO86, molecular mass, obtained by cooling the melt at 10 degrees Celsius per minute from the melt. The images show the different solid-state morphologies that develop based on the molecular mass of the MBC. The high molecular mass sample, EO155, exhibits a mesophase-separated morphology with distinct round domains embedded in a matrix rich in soft blocks. In contrast, the low molecular mass sample, EO86, shows a more homogeneous lamellar arrangement with no distinct domains. Significance. Figure 18 demonstrates the influence of molecular mass on the solid-state morphology of MBCs. The high molecular mass sample exhibits mesophase separation, while the low molecular mass sample shows a more homogeneous lamellar arrangement. This highlights the importance of molecular mass in controlling the structure and properties of MBCs. Figure 15 shows TEM images of two MBC samples with similar chain microstructure but different mass average molecular mass. The images reveal different solid-state morphologies, with the high molecular mass sample, EO155, exhibiting bright round domains within lamellar sheaves, indicating mesophase separation. In contrast, the low molecular mass sample, EO86, does not show these round domains and exhibits a more homogeneous lamellar arrangement. Rheological measurements of the samples also demonstrate that the high molecular mass sample exhibits a stronger deviation from time-temperature superposition, indicating mesophase separation in the melt state. These results highlight the influence of chain microstructure and melt state on the solid-state morphology of MBCs. The paper discusses the chain microstructure and morphology of statistical multiblock copolymers synthesized using chain shuttling copolymerization (CSC) strategy. The authors highlight the versatility of the CSC strategy in producing multiblock copolymers with tunable properties by controlling the comonomer content, block length, and relative amount of hard and soft blocks. They demonstrate that the complex compositional heterogeneity of these copolymers can be unraveled using different analytical techniques, including solution and thermal fractionation, TEM, and SAXS. The authors also discuss the relationship between chain microstructure and the solid-state morphology observed, highlighting the effects of crystallization and mesophase separation. They emphasize the importance of understanding the chain microstructure for predicting and controlling the properties of these materials. The authors conclude by stating that statistical multiblock copolymers have the potential to be important materials of the future, but further research is needed to develop cost-effective synthetic strategies and explore other classes of multiblock copolymers with functional groups for recycling. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.